So welcome back to machine learning, and today we do a midterm review. So the midterm is on November 19, and I made a post on eClass, which people should have got now, with details about the midterm, similar structure to the last one, but different content, and I guess there's going to be like stuff about actual machine learning algorithms and stuff this time around and whatnot, but yeah, like pretty similar style, I guess. And maybe one thing to mention is that I talked about how like the midterms are similar to the assignments, but this time around there was 2 assignments that were coding assignments. So you're not going to be expected to like write code on the midterm, or like you wouldn't really be selecting like what Python code is syntactically correct and stuff like this. But what you should understand is like some chunks of pseudocode similar to the course notes, and you should definitely understand all of the like discussions and kind of plots from these assignments. So that'll be very useful, because you can definitely expect to see questions being like, if we did this procedure similar to the assignment and you see like a plot like this, which of the following is like a correct kind of interpretation of what's happening and things like this, and you would have to select the things. So yeah, that's important to know. And I'll be going through like this in the tutorial today, so you can rewatch that when you study and things like that. Okay. But what I do in the lecture today is going to be just reviewing all the content that we covered after the previous midterm. And this is what this midterm too is really going to focus on. And yeah, so why don't we get started with that? Okay, so midterm exam 2. So it's going to cover sections, basically whatever we ended from last midterm, which is like the closed form solution for linear regression onwards till map. So let's start with that. So this is where we started after the last midterm. Linear regression, and it's like the closed form solution part. And okay, so all these notes are going to be pre-written, and I'm just going to like discuss and maybe write some things along the way. So this is the setting that's we've seen many, many times, and it's all that we're going to talk about really in the midterm is this regression setting. And this means that your features are always in this R of D plus 1 kind of set, this vector space, and your labels are R. Okay, this is almost always going to be the case. And in our algorithm, which is mainly going to be this ERM algorithm, but we get to map and Emily later, there's going to be something called a function class, and it's going to be a subset of all possible functions, or all possible predictors. Okay. And when you run the algorithm, you actually just get a specific data set. So you have this like D, you have the data set. And for ERM, we had this like estimate of the true expected loss L. So the estimate was L hat, and it was an estimate of this L. It was just the sample mean. And our goal was really to find this F hat that minimizes the estimate of the expected loss. That was our goal. And we said the way to do this is not to search through functions, but to search through parameters that are like unique, that each parameter uniquely identifies a function. And so the way we did this was we said, okay, let's make the function class this special set of functions, which are these linear functions, which can be identified by a parameter. So every function in the function class is identified by a parameter. And this is kind of a trick we use throughout afterwards, which is like, now we can think of every function as just being identified by a parameter, and then we can always solve all these optimization problems by optimizing over your parameter W. And that is what we did, and that was what our closed form learner did. It was just the closed form solution of the optimization problem here over parameters. And in particular, what we got was that our learner then outputs this F hat, where this F hat was like this linear function, of course, because it was from our function class. And this W hat thing had a special form, which was called this closed form solution. And these things had a definition. And like, if it's not on the formula sheet, you can, I also shared the formula sheet if you want to look at it. But if it's not on the formula sheet, you can expect that I will give you the definitions of these things like within the question. I don't expect you to remember what these are. Okay. And so the algorithm was quite simple. It was just like you had a data set, and at least a pseudocode. Then you need to compute these two matrices, or well, this matrix and a vector. And then you just calculate W hat by this equation, and then you output your predictor. And that was it. And the beautiful thing with this closed form solution is that you really got the argument of this thing. You really got the minimizer, the exact minimizer. There's no approximation or anything. The only approximation was the fact that you minimized L hat and not the true L. And so the way you think about this is like your algorithm your learner, which is really your algorithm, is going to output a predictor, and the predictor is trying to best fit the data. So if these black points are all your data from the data set, your predictor is fitting the data the best in terms of this squared loss, which is what we've been working with. Okay. So you can think of visually like this. Then we moved on to gradient descent. And it might have seemed kind of silly to work with gradient descent when we had this closed form solution. But the motivation I used for this, and it's not as clear for the problems we deal with in this course, but like in future down the line for machine learning, what you will find is that the function you're trying to optimize, like that L hat function, yeah, I'll answer the question in a second. The L hat that you're trying to optimize over might not always have a closed form solution. And so like a simple example is if this is like, okay, this is just some arbitrary function g, but if g was this like w squared e to the w, what you'll find is that it actually is convex. You can very clearly see from the plot, but you'll find that there is no closed form solution, meaning you can't write w as a function of these like elementary functions like cosines and polynomials and things like this. And so that was the motivation for then using gradient descent, which is not finding a closed form solution, but doing this in an iterative way. Okay, and now I answer the question, which was about the closed form solution stuff. So is the closed form only for linear functions? And the answer is no. So like, it also works for the polynomial case, which we see. Like for the polynomial regression, you also have the exact same closed form solution, except now instead of having x as your features, you have the phi of x. And then there's other cases as well where you can have a closed, like for the regularized version, you can also have a closed form solution, but we didn't cover that. But you can derive it. And yeah, so it depends on what your function class is. Sometimes you can have a closed form solution. And it also depends on the loss you pick. So this L thing, if it's not the squared loss, you might also not be able to have a closed form solution. So really, it's going to be like, what is your L hat? And L hat is really dependent on the L you pick, the loss you pick, and the function you're going to put in here for the function class. And yeah. Okay, so back to gradient descent. So we want to solve for the minimizer of a function that doesn't have a closed form solution, such as g of w. But you can clearly see there is some minimum here that you would like to solve for. And the idea was to approximate. Okay, so then there was two ways to do this. There was this like second order and first order gradient descent. And the second order one is like, in terms of getting the solution, is actually more efficient and powerful, but it's computationally kind of more problematic. So let's do the second order one first. And the idea here was, if your g of w, you can't find the minimum of it, why don't you approximate it with something that's actually convex and you can find a closed form solution for? And what we did is we approximated it by a second order polynomial, the following. And the way we got that polynomial was using this approximation thing called the Taylor approximation. It gives you some approximation to the function you're trying to approximate. And yeah, so there's this equation. Once again, you're not going to need to know this thing unless like I will explicitly give it to you. Okay, but the point is, there is this you should understand that there was an approximation, and after you have this approximation of your function, you can then solve for its like the minimum of this function, its closed form equation. And the way you do that is you just take its derivative, this is what the g prime is of this new approximation, set it to 0, and solve. And what do you solve for? You solve for w. And you get the following equation. So this is actually the closed form solution for the minimum of this function, which is our approximation. And what you find is that, okay, so this gives you like an approximation, and you can actually iterate this over and over again, because your approximation has to be based on some point w naught. So you could just keep getting a new w by solving and then replugging it in over and over again, and we get this general equation as follows. So you can iterate over and over and over again, and what you find is that as this new point, your new w, approaches, okay, sorry, as t goes to infinity, so as number of iterations goes to infinity, the point that you get from your solution approaches w star, which is the true argument that you're trying to find. Okay. So unlike the closed form solution, you don't quite ever get to w star for sure, but you get closer and closer and closer as t goes to infinity. And like you can get to it sometimes. It's just that like there's no for your specific problem, it might not be the case unless you iterate infinitely long to get right to the minimum. Okay, so there's this kind of loss in precision, but nonetheless, usually you get something very, very good. So this is okay. And then we mentioned that like, okay, computing the second derivative, which was necessary for this solution here, can be quite costly and complicated. when you have higher dimensions. So when you're dealing with vectors, vector inputs, these w's are vectors. And this thing is no longer just a second derivative, it's this thing called a Hessian. And we don't want to discuss it in this course, but the point is it's complicated to calculate. And so what people, one solution to this is to not use it at all, but just have a guess of what it might be by just one number. And this is called first order gradient descent. So you don't use the second derivative, you only use the first derivative. This is where the first part comes from. And so, yeah, you replace this 1 over second derivative with just this eta, which is called now your step size. And the reason it was called the step size is because we had this interpretation that what you're doing is you start with some parameter w, and you're constantly updating it to some like w of t plus 1 by taking steps of this size. And there's steps in this like gradient, which in the one-dimension case is the derivative direction. OK, and so in the multivariate case, things look very similar. Our new objective was no longer it wasn't to find a single parameter, but it was to find like this like tuple of parameters, which we call it a vector. So we want the vector that minimizes our function. And so now our function takes in as input vectors. And our goal, yeah, is to just find the vector that makes the function the smallest. So similar to before, but now we have a vector solution. So we need to find like w1 star up to wd star. One thing to note, so this is still like the kind of not machine learning thing. So notice there's no w naught. This was just dealing with like general functions. When I get to the machine learning stuff, there's going to be a bias term. OK. So yeah, and the procedure is the same here for this gradient descent business, which is your gradient descent update rule looks almost like before, except now we have an actual gradient here, because the parameter here, w, is actually a vector. And so there's a partial derivative for each index of that vector. So in particular, the gradient looks like this. There's a partial derivative for each index, right? W1 up to WD. OK, but then the update rule is virtually the same. And so for the multivariate case, we only deal with this first order gradient descent stuff. OK, so this is a method to find the minimum of some function. But why did we? OK, well, before that, OK, there's these step sizes now. There's different ways to pick the step size. Ideally, you'd want it to be this Hessian thing, but I said that's costly. So there's kind of like some in-between methods that give you approximations to it, each to various levels of accuracy and quality and so on. And we talked about 4, and there's much more elaborate and complex ones. And this is quite a big discussion in machine learning world where people really care a lot about the step size because it makes a big difference. So there's all sorts of different methods. And in these machine learning libraries, you can really just plug in and choose different ones. Yeah. But we talk about some simple ones. So the simplest one is this constant step size, which is literally over all epochs t, you just have the same number. So you're maybe 0.1. So you take steps of this 0.1 scale. Then there's this inverse decaying one, or exponential decaying one. And the idea is that as the epochs increase, with as you get further in time, more iterations have been done, you want to decrease your step size because you assume you're kind of closer to the minimum, and you don't want to overshoot the minimum. You should be taking smaller steps. And then there's finally this normalized gradient one, which depends on this, basically the magnitude, or this is called the 2 norm of the gradient. But it's really just the size of your vector. If your gradient is really, really large, you should maybe scale with the inverse of it so that you don't overshoot as well, because you don't want to take a really, really big step in the case where your gradient's really large, right? Because if the gradient's really big, then you're going to take a giant step. So you want to make the step size kind of be 1 over this gradient, sort of. Anyways, there's just these 4 methods. OK. But the point is they're all trying to really get as close to this second order version of gradient descent as they can. OK, then we went back and actually did machine learning stuff, which we said, how does gradient descent look for our data and the estimate of the loss and so on. And what that really looks like is now your g function is just L hat, and that's it. So instead of optimizing over g, you have L hat, which is your estimate of the loss. That's just a function. It looks like this. It's just some function of w, and this is for the linear function case. And you can this is its gradient, and you can just do gradient descent with it. And the algorithm was quite straightforward as well, which is you have all these iterations. So you kind of pick the number of epochs you want to run beforehand. The longer you run, the better your solution is going to be, but then obviously you need to run for longer, so it's going to take more computation. And for like real world problems, this gets into like the weeks or like the days or weeks, and it costs a lot of money to run because you use these GPUs and so on. So this is like a real constraint, this compute stuff. In our case, like it takes a couple seconds or minutes. So we really, it seems silly. It's like why you'd set t really, really large, right? But yeah, there is a real constraint when you get into more complex algorithms. Okay, and the procedure is just, yeah, calculate the gradient of your function and then take steps as follows, which is the exact same kind of gradient update rule. This is in your formula sheet, this rule. It's like very important to kind of know what it's doing. Yeah, and then you just, after you finish these t steps, you just output the predictor that uses essentially the last parameter you got to. And this should be pretty close to the actual argument. Okay, so that was the gradient descent stuff. And visually, you could think of it like this, which is you had this data, like these black points, and the actual closed form solution was this, and it gives you the best possible fit. But gradient descent, what it does is after every iteration, you get something that should be better and better than before. And so what you can think of is at the beginning, for your first parameter, W0, at like the first epoch, you have a terrible fit. Like this line doesn't fit the data at all. And then maybe after 5 epochs, you have something that fits a lot better. After 10, you get something even better. And as t goes to infinity, you'd get this actual, like, you get really, really close to the closed form solution. OK, so that's how you should think of gradient descent. It's always getting as close as possible to this closed form solution. Or sorry, it's getting closer and closer as the number of epochs increases. And then we had a brief discussion of like there's another potential advantage to gradient descent other than the case that your function you're optimizing over might not have a closed form solution. And that is just computing the closed form solution alone might take more computation. And we saw that by noticing that the closed form solution requires this kind of computation, this like n d squared, d cubed thing. But the batch gradient descent algorithm required n times d times t. Anyways, the important point is that if the number of epochs is much lower than the dimension, which is possible for some settings, like your number of features could be extremely large, then then batch gradient descent is what I write? I wrote batch gradient descent is more computationally efficient. Yeah, and that's just like these couple math steps here. Basically, you replace t by d here, and then you find that, yeah, it's upper bounded by this guy. Okay, so that was batch gradient descent, like potential benefits of why you might want to use it over the closed form solution. And then we said, okay, like maybe there's like another idea of how to make batch gradient descent even more like computationally efficient. And that is that if you go back to the batch gradient descent algorithm, you notice that each gradient, you need to compute the sum over all the data points n. And what you find in real world problems is n can be very, very large, like in the billions or whatever. And so to just take one gradient step, this computation can take really, really long. And it turns out one trick is not to take gradient steps with respect to all of the data, but to break up your data in things called batches, mini batches, I guess. And that visually just says, like, think of your data set as being split up into these mini batches. So here you have mini batch 1, mini batch 2, up to mini batch m here. So the number of mini batches is m, which is just the smallest, basically the smallest, like the nearest integer rounded down of number of data points divided by batch size, mini batch size. Okay, and here, importantly, for this course, we don't use the data points. We don't use the last like n minus mb data points. I don't know what I wrote here. Let me just erase this. Okay, so yeah, we don't use these data points if you end up with some like leftovers in your last mini batch. And this is just to simplify things. It's not without much. It's not like you don't lose much. It's just one mini batch that's quite small that you lose on. Okay. And the important thing is that what we get from using these mini batches is that the estimate of the expected loss is now based on less data, so computing it is much easier. It's only based on b data points, right? So it goes from m minus 1 times b to m times b, which is just b data points. You think of that as using one of these chunks here. So from like 1 to b, or b plus 1 to 2b, and so on, one of these mini batches. And so you use that for your estimate of the expected loss. And what that buys you is now in your algorithm, instead of just taking gradient steps each epoch, which is here, what you do is you take gradient steps more frequently. And the way to do this is you have another extra for loop inside, which breaks up your data into these mini batches. So for each mini batch, you then calculate the gradient and take a gradient step. So the gradients are a worse approximation, but you can take more frequent steps. You get like actually capital M more gradient steps. And so we didn't get into like the theory of when this is advantageous and so on, but it turns out that usually this is beneficial in practice. And yeah, the advantage is in that you can take more of these gradient steps, although they are like more incorrect, like these approximations of this gradient are technically less correct than before because it's based on an estimate L hat that uses less data points. Since you can take them more frequently, it turns out to be beneficial. And there's these kind of two extremes, which is that if your mini batch is all of the data, that means your mini batch is of size n, then you just get back the original batch gradient descent, which just takes a step using the whole batch of data. However, if your mini batches on the other extreme are just of size 1, so you literally just use one data point to calculate the gradient, so you wouldn't even have a sum here. It would just be like this would be 1 to n, and then you would have xm here. So you'd be using one data point each time to calculate the gradient. This is called stochastic gradient descent. And what you usually find is that something in between these two extremes is kind of the best. Yeah. OK, so that is the end of this gradient descent stuff. And let me answer a couple of questions. So would you prefer B for mini batch to be as small as possible for accuracy? So let me just maybe answer this. So like, if you want the estimate of the loss to be as best as possible, you want B to be as large as possible, n. But what you suffer with doing that is that you take less gradient steps. So there's this trade-off in terms of the quality of your L hat and how many gradient steps you can take. So if you want the best possible estimate, you use all the data, but then you take less steps. However, if you want to take more gradient steps, but a less accurate estimate of the expected loss, because you only use like one data point, you would set B to 1, and then there's something in between. And it says like, is mini batch gradient descent in general better in general than batch gradient descent? And yes, like so in practice, people will actually use batches of something of size like 32 or 64 or 128. These are quite common batch sizes. And then they don't even call it mini batch gradient descent. They just call that stochastic gradient descent a lot of the time. So they'll say we're doing like stochastic gradient descent with batch size 32, which is kind of abusing this notation. But yeah, that's what you'll hear in practice. So people are not using like batch sizes really over like 1,000 or anything. And taking more gradient steps helps because of the idea of like each gradient is getting closer and closer to the minimum. So like we had this whole discussion here very briefly, which was you really want to take as many gradient steps as possible because as t goes to infinity, you get closer and closer to W star, the true minimum. So like ideally you just keep taking them. And so yeah, the more gradient steps, the closer you're getting to this minimum. OK, so let's move on to polynomial regression. And so in polynomial regression, we said basically like maybe we should do something other than linear functions for our predictor. Like maybe like in 1D, a line is not always going to be the best fit to our data. Maybe like something like a quadratic or like a cubic. The data could follow a more complex trend than just a line. And the idea was that, OK, you could like, we didn't really say this, but like you could somehow like decide that your function is a much more complicated like function class, which we kind of did, but then like say like, oh, you need to learn these parameters, which are somehow much more complicated and related to each other than before. But what we did is we kind of did a trick, which is we said, let's just change the features we have. So let's take the features and transform them into some like more complicated looking features in this polynomial transformation, or this polynomial feature map. So we said, let's take our features from the feature space X and move it to some new space Z, which is going to be of larger dimension, and it's going to allow us to capture different kind of relationships between features. So for instance, maybe one of the features like follows, like the actual data follows that feature squared kind of trend, or it like there's some relationship between features, so they need to be multiplied and so on. So this is what this polynomial features allow you to do. And in particular, this new space it maps to is this like R of P bar space, and P bar has this equation here, which we didn't talk about the details of how you get it, but it's on the formula sheet. And the point is that P bar will definitely be larger than D plus 1. So you gain new features, but these new features are really based on the old features. They're like multiplying the old features in all sorts of different ways. And the question about this is initially for D equal to, yes. So like, oh, sorry. I'm not sure what you mean by D equal to 1. So like what we've been doing before is that we've always been doing P equal to 1. And now what we've done is we say we're now dealing with polynomials of degree larger than 1. So yeah, everything up to this point so far, like everything above, was with P equal to 1 you could think of. It was doing polynomial regression, but with polynomial degree 1 features, which is just linear functions. And now we want to introduce functions that are like technically nonlinear in terms of like how the features look, because the features are now can be these different multiplications of each other. Okay, so this allows you to describe more complicated looking functions, and the function class is now this like FP thing, where P indicates the degree of the feature map we use in here. But the beautiful thing of doing it this way, where we just transform the features in this very fixed way, right? So we choose how this like we choose that, okay, I want to do a polynomial degree 3 transformation. So I'm going to use phi 3 here, let's say. I choose this beforehand, then I get new features, and then I can think of everything as just being a linear function of these new features. So everything looks the same as before. Okay, I just want to point out one thing is like, this is in contrast to actually what happens in neural networks and things like this, where there you don't fix this function and you actually learn the transformation. That's where things become more complicated and stuff. But here we choose beforehand, like, okay, I want to use this specific function. Why should I use this? Well, maybe I think for some reason the relationship should be a 2nd degree polynomial or a 3rd degree one, or for whatever reason. But like you're kind of just taking a shot in the dark at the features you think are the best. Okay. But anyways, yeah, okay. So that's the story. You allow yourself to model more complicated functions with a bigger function class, and you have this relationship where each time you increase the subscript here, you're adding polynomials of a higher degree, and so each function class f2, f3, and so on to fp gets larger and larger. So it contains all the functions from before, but even new functions like of higher polynomial degree. Okay. And what that really implied was now your estimated loss, L hat, if you pick f hat of 1, which is the best, let's say the best predictor from f1 here, then that estimated loss will always be at least as large as that of f hat of 2, because f hat of 2 had the choice of being any function of polynomial degree 2 or higher, or less, which could have very easily just been f hat of 1, but potentially could be a better predictor. So it has basically, there's more predictors to pick from in this function class f2, and so on. So as your function class gets bigger, which is what's happening here, the function class gets larger and larger, then you can make the estimate of the expected loss smaller and smaller because you have more predictors to pick from. So this should make sense. And eventually, as you go to P being really, really, really large, then it turns out the polynomials can actually model any possible function. And so then eventually you can just minimize L hat to be like essentially 0, because you could just pick the predictor that makes L hat 0. Okay, so that was the story. And the way you can think about this is like you have some data. This is your actual data set here, maybe 5 points. And as you increase the degree of the polynomial, so like we start with degree 1 polynomials, it's a line, and this may be your best fit. Then if you have quadratic polynomials, so this f2, then maybe this is your best fit. But if you take P really, really, really large, what you can get is a predictor that perfectly fits the data, and so you'll have virtually 0 estimated loss. And okay, then you achieved, like you made the estimated loss really, really small. But then we got to the next part of the course, kind of, which is asking like, is this really a good idea? Like, did we actually achieve our goal in machine learning, which is to, like, roughly speaking, is to predict new data well. So if we got like a new feature, would we actually predict things well? And so that was the next part. So that was this whole like evaluating your predictor or model, and then trying to use like, if we can evaluate how well it's doing, then we can maybe pick the right learner to use. Okay. So how did we do this? Well, we said Well, we said let's get back to our what's our objective in machine learning, and I said like our objective is to like predict new data well, and the way we mathematically describe this is saying something like there's an expected loss, right, which is like how much loss you expect to suffer if you were to see new data points in expectation over all possible new data of our predictor. And then since like the data set might be different, we want to be small on average or an expectation over all possible data sets we see. So this is like really our predictor, because like we don't know the data set we're going to get, and then we don't also know the new points we're going to get in the future. So we want to do well on new data in the future over any so we want to do well on new data in the future. That means in expectation over the future. That's what this expected loss captured. And then we also want to do well, like our learner should do well no matter what data set it gets, kind of. So we want to do well in expectation over all possible data sets that the learner gets, which is captured here. Okay. And so that was kind of our goal. And then how did we think about how do we like break this up or think about this term? Well, we ended up with like decomposing this into some error terms. But before we did that, I wanted to like mention what was our algorithm. And the algorithm was this like empirical risk minimization business. And what did ERM look like? Well, it said, first of all, since we don't have the expected loss, which is the thing we really want to minimize, let's get an estimate of it, L hat. And then why don't we minimize that? And in particular, let's pick a function class to minimize over. And like one reason to pick this function class is because if you don't pick a function class, it's really hard to solve the optimization problem, because things might not be convex like we saw before, or like before things were convex specifically because we picked these linear functions. But if we didn't, then we might have like further problems. Okay. So we had these two things, and like really kind of roughly speaking, when would you expect ERM to do well? Well, it would be if the function class that you picked actually contained the predictor or function that made the true expected loss small. Okay. And second, that if the thing you were minimizing over, which is the estimate of the expected loss, if it was actually a good estimate of the true expected loss. Okay. So basically, you should include predictors like that. You'd want to include the predictor that actually minimizes the expected loss. And second of all, the thing you're optimizing over should hopefully be a good estimate of the true thing you want to optimize over. This is like the high level idea. And then we really saw this more formally by just like decomposing this term into these different error things. Okay. Yeah, so, okay, maybe I tell you the decomposition first, and then I come back to this part here, because I think it makes more sense. So this is what we did. We decomposed our objective into 3 error terms. And this was like all we did was just add in. So we started with this. This was our goal. Our learner outputs an f hat of d. It outputs a predictor. And we want to know like what is its expected, what is the expectation over data sets of the expected loss. And the way we did this was we added and subtracted the expected loss of something called f star, which is the best function in the function class, meaning the function that actually minimizes the expected loss, but only in the function class. And then we added and subtracted the expected loss of f base, where f base is the best possible predictor, where you can pick predictors to be any possible function. Okay. And we called these terms the estimation error, the approximation error, and the irreducible error. And these terms, hopefully the names like kind of made sense. Whereas the irreducible error is really the best you could possibly do, because f base is really the best possible predictor. It's the smallest any predictor could possibly make the expected loss. And so this is like due to the inherent kind of noise in the labels, which is like for a specific feature, there could be many possible like kind of labelings. So that's like if you look at houses with 3 bedrooms, there's not just one price that they will be sold for, there's many different prices. And the way to like improve this error is to actually just gather new possible gather new feature information. So maybe you could gather like the size of the house, where it's located, this kind of new information, and that will allow you to better predict things, and the noise will be reduced. So that's the idea. But usually you can't gather this new feature info, and so people call this the irreducible error. Then there's the 2 errors we actually talk about in this course about how you like reduce and how to fix, and this is like what people really focus on in machine learning, is the estimation and approximation error. And the approximation error is the error due to picking your function class, basically. Like if your function class does not have good predictors, like ones that are close to f base, then this thing will be large. That's the main idea. And so we saw that here, like approximation error it decreases if you make your function class bigger, because you might have a better, like it might include a predictor that's closer to f-base, basically. And then finally, there's this estimation error. And this is due to the fact that you're using L hat as your estimate of the expected loss. And so you're picking your predictor f hat based on L hat. And so what we found is that this thing decreases if you increase data. This should kind of make sense. If you have more data, your estimates and stuff will be better. But also it will increase, so it gets worse. This is the opposite of the case for here. So it's increasing now if you increase the function class. And the idea here was that it's going to do this thing where we call it overfitting, where it can, because there's way more functions to pick from, the function you end up picking might be one that really, really fits the data quite well. But if you don't have enough data, then that might mean that, like, for new data, it doesn't actually do well on new data. Okay, roughly, like, okay, so that was the thing. There was a lot of like pictures and stuff to describe this, so maybe I don't go into too much more detail. But these are the relationships. These are pretty important to know for the midterm. Like, yeah, this is not on your formula sheet. This is just like part of things you should understand and why. Okay. And yeah, you can just like visually, like this is on your formula sheet, and so you should be able to like visually kind of remember what's these things are comparing. Okay, and then finally, like there was this discussion of like how do we think about this estimation error to have these properties, and that was that you can do this like extra decomposition business, but basically you can show that because you're picking your predictor f hat based on data. So you're picking f hat based on the actual data, then each one of these like L of f hat terms are not independent of each other, because f hat itself actually depends on each one of these data points. Okay, and that kind of like should make sense visually, at least what we saw before. Like if there's these data points and you fit the predictor that like fits perfectly through everything, then it should be no surprise that if you see new data, it probably won't fit it perfectly anymore. And in particular, we see like the expected loss of our predictor f hat compared to the estimated loss, which is the thing we actually minimize over. This difference increases as the function class gets bigger. This allows you to overfit the data more, but it decreases as n increases. So if you have more data, then like even if you did overfit the data, if you have so much of it, then it's probably representative of what new data will look like. Okay, and before answering the questions, I just go into finishing this, like these error decompositions with this plot, which is, you should think of the error decomposition, again, this is just rewriting what we saw, and thinking of estimation error as the difference between the estimated loss of our predictor f hat and the expected loss of the predictor f hat. And so there was this plot. And so let's just really quickly talk about this plot. So there's the expected loss due to f-base. This is the minimum possible expected loss any predictor could possibly get. It doesn't change with polynomial degree or anything, right? So here we're plotting the complex, like we're plotting things as a function of the, or as in terms, like the x-axis is the complexity of the function class. As p increases, your function class gets more and more complex. So what should we expect? Well, we should expect that f star, so the expected loss of f star, is going to get better and better if the function class gets bigger and bigger, because there's a better predictor to pick from. And f star is the best possible predictor from our function class. So that's what we see with this green line now. You see that as the function class gets bigger and bigger, eventually it's getting closer and closer, and we'll eventually get to f-base, which is the best possible. Because eventually, if you make your function class big enough, you're just going to have f-base in it. Okay. Then what we actually have to work with is this L hat, this is what our predictor is actually working with. And it's minimizing L hat. So unsurprisingly, if you increase the function class as well, you find that your predictor, your output, is making the estimate of the loss also smaller. This is what we saw with like the polynomial regression, is that as the polynomial degree increases, our estimate of the loss is getting better and better. But what we find is that unfortunately, although this is getting better and better, the error between the estimated loss and the true expected loss of our predictor is getting further and further. And this is because the function class is getting bigger and bigger. And so you would see this by like at the beginning, this difference isn't very large, but then it gets bigger and then bigger, and eventually it gets even worse. So there's this battle between making the function class too large, because then these, like basically this is what it's called, oh, you're overfitting the data. You're making this estimated loss really, really small, but in reality, your expected loss is very, very large. This is the overfitting side here. This is really big. And then you're battling also between having a function class that's way too simple, in which case, even if your L hat and L are really close, which they are here, the problem is that the best possible function in this function class, which is this F star one, is really, really large. It's just like your function class really does not contain a good enough function to model F base. So this is like the kind of classic plot you will see. OK, now answer some questions. Yeah, so all the polynomial function classes are, the question is about convexity of the polynomial function classes, and they're all convex in the new features. So like you get these new features where the polynomial features and they're of dimension p bar. And then if you think like everything is convex in terms of those features, or in terms of like those, like you're going to have a new w, which is of dimension r to the p bar. And in terms of that parameter, everything is convex. Yeah. So that's OK. Yeah, that's all I have to say about that. And then it says, when we make f larger, is it more functions? Is it just more functions in the set f? And how would that be possible? I'm not sure what that means, but like if you make the function class bigger, then you include new functions in the function class that you didn't have before, and you keep everything there from that you already had. So like in the polynomial case, when you increase the p here, then this phi of p is a function that includes all of the features you had before, but then new ones. So you could always model everything from the previous function classes. So these, like the correct word of being larger and stuff is really there's supersets of the previous function classes. Yeah, so I think, and to answer the phi part, it's like, yeah, things are linear in terms of phi. So you think of phi, like the output of phi as your new features, and then everything is linear in terms of this. Yeah, so they're linear functions of phi. OK, so let us continue. OK, so we had this great plot about thinking about how to like, OK, what really did this allow us to think about? This allowed us to think about what function class should we pick. OK, because like, OK, like for data, what we found is that for data, you just always want to gather as much data as possible. The only thing that data affects is the estimation error, and it's always beneficial to gather more data. So then you have this trade-off of the function class you want to pick. And it's like, if you want to pick f really, really large, then OK, you decrease approximation error. But then if you pick it really large, you increase estimation error. So there's this battle between picking your function class. And you need to pick a function class for your learner. And so this plot, what it tells you is that, well, if you're going to pick you're going to pick a learner, and that means you really pick a function class that your learner uses, and then that learner is going to output a predictor, and that's the predictor you're going to pick. But like, how do you pick that function class? And what this says is something like, try many different learners. And that means like try a learner with a function class of polynomials degree 1, and then another one with polynomial degree 2, and 3, and 4. So you'd run like 7 different learners, because there's 7 different things. They'd each output a predictor, and then you would pick the one that has the predictor that had the smallest like expected loss, if you could calculate this. But then the problem arises that you can't calculate the true expected loss. And so we are going to estimate this thing. And we're not going to estimate it in this bad way that we were doing before, in terms of like using L hat with the actual same data that we base F hat on. But the idea is to have a new set of data that your predictor is not based on. OK, because if it's based on the data, then that's a very bad representation of how it's going to do on new data, it turns out. And so the idea is that we can't gather new data, but we can split our data up into training set and test set. We still only use our data set. So we go from 1 to n minus m for the train set, but then n minus m plus 1 to n. So we still only use n data points. That's our data set. But we only use this train data for our learner. So our learner only uses the train. And the test data is purely reserved to evaluating the predictor our learner outputs. And in particular, we're gonna have like multiple learners you would train. So you would have like actually a learner with degree 1 polynomials. Then you'd use a different learner with degree 2 and 3 and 4, each of them producing their own predictors. And then you look at the corresponding, what is called the test loss. It's the estimate of the loss based on the test data. And then you would like look at this plot and you would find that, okay, maybe in this example, the learner that used degree 4 polynomials is the learner that like produced the predictor that had the smallest test loss. And this should really be quite close to the expected loss for that predictor, because this is based on data that the predictor f hat did not use to train. Okay, so that's how you do things in practice. You have this extra set of data that is used to kind of evaluate different kind of learners. And this is like, this can get a little bit confusing because like what's really happening is you have like some sort of like meta learner you can think about, which is actually running like the gradient descent learner for like 7 different, let's say in this case, function classes. And then you pick the one that produces the best predictor. So you really are running 7 different learners. Okay. Okay, after that, we talked about another way to think about error, which is this bias variance decomposition. And this helped us think about regularization, but you could also use it to think about the previous case of the function class stuff as well. And this one had a similar story at the beginning where you get this irreducible error, but then the 2 terms are no longer estimation and approximation error, but they're now something called the variance and the bias. And here, instead of relating to this f star, we now relate to this thing called f bar. And f bar is thought of as the expected predictor. So it's if you take the predictor you get from the data set, f hat, and then you take its expected value over all the data sets. I don't have the plot here, but like the idea was like, okay, different data sets are going to produce different predictors by our learner, right? That makes sense. Like the learner is trying to best fit the data. If the data changes, then the best fit is going to change. So f bar is the function that the learner outputs kind of on average. So over all the different data sets, you have all sorts of different predictors. If you take their average, kind of like pointwise, this is what the conditional on x means. So for every input point x, you take that average of all the predictors, then you get this expected predictor. Okay. And it turns out that like for all the cases actually above, until we got to regularization, f bar is the same as f star. This should kind of also make sense. Like f hat is based on the same function class as f star. And then f star was the best possible function. And we're saying here that on average, our predictor will also be f star. It's just like for a specific data set, it might not quite be f star because it's going to overfit it. But like on average over all data sets, the errors kind of like cancel out. Okay. So anyways, roughly speaking, you can think of variance as being this estimation error because it's the difference between your predictor you output and this expected predictor. How much does the actual predictor you output vary relative to the expected predictor that you would output? And then the bias is thought of as the expected predictor compared to f base. So it's like how good is the expected predictor relative to the best possible predictor f base. And it turns out this you can think of as roughly being like this approximation error. Okay, so these are these 2 things. And the story in terms of how they are affected by data and the function class are the same, which is that the bias will decrease, right? Bias, how close is expected predictor relative to best possible predictor is going to decrease when? Well, when you increase your function class. So if like your predictor has more functions to pick from, like if your learner can produce a predictor from more functions, that means increasing your function class, it makes sense that the expected predictor would be closer to the best possible. Because you might, like at some point, you're actually going to be able to pick f base. It will be in your function class. And the variance has that kind of like the opposite story, which is that, okay, if you increase the function class, your variance goes up instead of going down. And the reason why is now like, if the function class is bigger, your predictor can vary quite a lot relative to its expected value. There's a lot of functions to pick from. And then finally, the variance goes down if the data set, like the size of the data increases. And this should also make sense. Like if you have enough data, then like no matter like even the predictor you pick for a specific data set will be very, very close to what the expected predictor would be, because there's just so much data that like on new data you don't expect it to change too much. So always like the thing to remember is increasing data almost like basically always helps. You always want more data. And the thing that you're battling with is picking the function class because it either increases or decreases bias, one or the other. Okay. And yeah, and then there was like a similar plot of this like overfitting and underfitting business and so on. But then we got to regularization, and regularization was like one way of thinking about it was a different way of picking kind of like the complexity of a predictor. So before, we could change the function class, and that would of course change the complexity of the predictor our learner could output. But another way to do this is through this observation that you can change how large the weights of your predictor are, and that will change its complexity. So there's this observation that large values of your parameters or your weights leads to more complex predictors. Okay? You take this for granted. Did I just tell you this? This observation people made, I guess. And if you know this, then what you can do is you can have a parameter called this regularization parameter that will penalize the size, like how big your weights are. And you can use this to tune how much you want to penalize these weights. So in particular, now we have a different objective, which is not the usual estimate of the loss, of the expected loss. We now have this thing called a regularized estimated loss. And so it's the usual estimated loss, this guy, based like the sample mean estimate. But now we add this extra term, which is going to penalize how much, it's going to penalize how large the weights are. If you make lambda really, really large, then making the weights even slightly larger than 0, you will suffer a lot for that. And so the solution that makes this as small as possible, like the W's that make this as small as possible, this whole thing, will be the W will be probably very, very close to 0, because otherwise this term is really large. And on the other hand, if you make lambda really, really close to 0, you basically get back the previous version. So if you set it exactly to 0, then this goes away, and then you're just left with the previous version of what we were working with. Okay, so you get, like, what I mean is you just have linear regression, not regularized linear regression. And yeah, so then the thing that changes is now our thing to minimize with all of our optimization, like gradient descent, or if you try to do the closed form solution, the function that we're optimizing over is just different. It has this extra term. And yeah, and the properties in terms of bias and variance are as follows, which is that you will find that the bias, okay, is going to decrease if lambda decreases. Okay, why does that make sense? What happens when lambda decreases? When lambda decreases, you penalize the regularization term, or like the weights being large, much less. You basically say, okay, if these are really large, doesn't really affect me because it's getting multiplied by such a tiny number. That's lambda being small. And what does that mean? If the weights can be really, really large, that means your function, like your predictor, can be quite complex if weights are large. And if the predictor can be quite complex, it means it's more likely that you can model f-Bayes quite well with a function in your function class, and in particular, the expected predictor. So that's what it allows you to do. And the other case, so that's the bias gets smaller. Your expected predictor can get much closer to f-Bayes. You're not really restricting the expected predictor to be simple. But if you make, okay, here we kept the same structure. So he said, however, if lambda is really small, which is the same thing as here, so maybe I should say if lambda is small for the variance, then what you'll find is that the variance actually increases. So there's this trade-off now from bias and variance. And why would that be the case? Well, like lambda being small means your predictor can be quite complex. And so if the predictor can be quite complex, it can vary quite a lot relative to the expected predictor. So your predictor can vary a lot from the expected predictor. If lambda, on the other hand, is really, really large, then your predictor would be very, very simple. And if the predictor is very, very simple, then it can't vary much relative to its expected predictor. It doesn't change much relative to data. However, the bias would then be very large, because if it's really simple, then it's probably unlikely to model f-Bayes well. Okay. And finally, if the n increase, it's the same story as we saw before. Your variance, like n increasing is always good. It decreases variance. Okay, and the plot you see now is, instead of plotting polynomial degree, you plot regularization parameter. And I did want to note in the tutorial, I'm also going to go into more detail about this regularization stuff, because if someone was asking on Piazza. So you can watch that if you want more details later too. Okay, so yeah, now instead of plotting the polynomial degree, we plot the regularization parameter, and we plot it in the inverse direction. So here, this is large on the left-hand side and gets smaller on the right. And the reason I do this is so that the plot looks the same kind of as before. And so you think large lambda means simple predictors. Small lambda means complex predictors. It's very similar to when p was small. So in polynomial degree, when you had p like equal to 1 here, you could only output simple predictors like lines. And here, when p was large, like we had p equal to like 7 or something, then you could output complicated polynomials. And then you have the same kind of trend, which is that, yeah, your train loss, this is called like your regularized train loss, it decreases. As you decrease lambda, you can output more complicated predictors. So of course you can fit your data better. But then you find that on new data, so on your test data, you then are worse off. And so there's this like, there's kind of like a middle ground, which you would pick over here, where this is not too far apart from each other. But also like, you can actually make L hat train quite small. Okay. So yeah, there's this overfitting, underfitting, and these are the two. Like overfitting happens when bias is low and when variance is high, and the opposite for underfitting. And there was like a brief question about why there's this observation of these weights being large. Why would this mean something's more complex? And like, yeah, roughly speaking, like one way to think about it is like, if you have, so like the thing, so here you're summing up all the weights. So like just one simple way is like, if you just remove some of the weights for like the larger degree polynomial terms, then this thing gets smaller, and you can think of just like you just removed some larger order polynomials. So okay, what I mean is like when this 5p, you can think of as like first it has all the linear features, and then after it has all like the second degree polynomial features, and then the next terms after are like the third degree polynomials and so on. And if the weights are smaller, then you can think of it's just like first removing the higher order polynomial parts, and then the less high order ones, and so on, until eventually like it only has some weight on the very beginning parts of the features, which are just the linear part of the features. So I don't know if that clarified things, but you can kind of think about it as like kind of removing the degree of the polynomials by just setting all those weights to 0. Yeah, and if you allow the weights to be quite large, then those like higher order polynomial feature terms that 5p produces can actually be scaled by something. We allow the weights to be something, and then it becomes more complex. Okay. After that, yeah, so that was okay. So we had this regularization stuff, and what our learner would do now is minimize this regularization business instead of the previous estimated loss. So we now minimize this regularized estimated loss. And so the objective, the objective is just as simple as you want to try to find the argument of this new loss. And this new loss is just like, it's the thing we saw above. And you can, there's a closed form solution for this that you can calculate. We didn't do it. But what we did is we used batch gradient descent. You could also use mini batch gradient descent to just find an approximation to this argument, right? Batch gradient descent gives you an approximation. If you increase the number of epochs, you get a better and better approximation. So for that, you just need to use this batch gradient descent update rule. And really all you need is the gradient of L hat lambda, which is this regular thing. So then you just need to calculate this. And we did this in class, and it has like, you have to handle the case where of like the 0th index of W different than the others, because we don't regularize J equal to 0. We don't regularize W 0. And the reason for that is that it turns out that like if whatever the value of the bias is, it doesn't change really the complexity of your predictor. It just scales your predictor up or down. And you want to leave that term. Like you want to be able to change basically the y-intercept of your predictor. So yeah, so that was that, yeah. J equals 0 not included, very important, because that changes the gradient update rule. And also the closed form solution would be a little uglier due to this reason. Okay, after that was all focused kind of on, okay, so far we covered this like grade optimization part of things and the evaluation part of things. And this all focused on really one algorithm, which was like ERM. Optimization just said, how does ERM do its optimization step, right? It had an estimation part, and then it tried to optimize. So here, like the optimization section really was asking, how do we do that? Now we just finished this evaluation section, and the evaluation section was saying like, okay, in ERM, like really we were just saying like ERM, you need to pick a function class. How do we pick that function class? And the story was like, okay, run ERM, your learner, for different function classes, compare its performance on the test set, and then just pick the predictor that did the best based on the test set. And then we said, okay, instead of thinking about changing the function class, we could just keep the function class constant. So keep it really large, like f of 10. That's what regularization lets you do. But then have this new parameter called lambda, which just changes how complicated like the predictor that ERM can output is. So now you can think of you run ERM, but not you keep the function class fixed, but you change lambda for ERM, which is like a new parameter now inside of ERM. So you change this lambda, and that really will change what ERM is optimizing over. So instead of optimizing over just L hat, now it's optimizing over L hat lambda. So that's how ERM changes there. And yeah, so that's what we were trying to address in this evaluation part. And like, why call it evaluation? I guess it's like, maybe it's not the best kind of name, but like, it's sort of like after we've learned how to do ERM in the previous sections, we now want to ask, like, did ERM do well? And what we observe is that like ERM, it depends on what the function class was for ERM. And so like, how did we learn that? We learned that by like evaluating the predictor, and then based on that knowledge we just got, we can then do these methods, which is like try different function classes and pick the best function class to pick the actual predictor. Okay, and maybe one more word I'll say is that in practice, this like extra step, right, of picking the function class and like trying different function classes or trying different regularization parameters, this is called hyperparameter sweeping. So people like call these extra parameters like the polynomial degree or the regularization parameter lambda, they call these hyperparameters. They're kind of like the parameters of the learners. And then you try different values of these, and they call it sweeping over hyperparameters. You try different learners with these different values of these hyperparameters, and then you pick the best one. Okay. Okay, after all that, we then moved on to another approach people have to, I guess, kind of machine learning stuff, and it actually comes, this is like more from statistics world. And so people in statistics, instead of like kind of naively saying, oh, let's just pick some loss function and then minimize that, they kind of wanted this like more principled way of doing things. And I motivated it in this way, which is that I said, okay, like if you wanted to make the expected loss as small as possible, f-base makes it as small as possible. So why don't we just find f-base? And it turns out if you assume the squared loss for your loss function and you assume the regression setting, you will actually find that this f-base is this like expected label given the features, which has this nice form, like there's just the definition of the conditional expectation. And it has this form where all you need is this conditional PDF. Okay. And so this is how I like motivated that, like, okay, maybe we can just approximate f-base in this way. We don't have to go through this estimate of the expected loss and so on. And it turns out that people in like statistics literature already have talked about this a lot. And what I mean is they've talked about how you estimate PDFs or PMFs. So they've talked about, and this is called the maximum likelihood or maximum a posteriori estimation. And this is all about estimating a PDF or a PMF. Okay, they want to estimate they want to estimate these things. And if you estimate that, then with that you can do anything, like you can do all sorts of things. One of the things you can do is plug it into this equation and get f-base, which is how we want to use it. Okay, so for machine learning world, like if you just want a predictor, you really just want to plug it in here to calculate the integral. But you could use it for other things, right? Like if you have the density, you can calculate, I don't know, the variance of it and things like this. But we don't need any of that. Okay. So then all we needed to approximate f-base was some basics of how maximum likelihood estimation works. And then once we know these basics, we just do it for our problem. And the procedure was pretty straightforward, which was like the setting of this maximum likelihood estimation is that you have some data and you assume that they're all IID. Like, okay, you have some data, you have n data points, you assume all of them are IID and they have some, so that means they have some common PDF or PMF, P of Z. And you assume that this PMF or PDF is based on a parameter. Why do you do this? Because like the only way you really know how to optimize functions, which is like a PDF and a PMF is just a function. The only way we really know how to optimize these things is by optimizing parameters. So once again, if there's like a unique parameter for every function, then you can just think about optimizing functions as optimizing parameters. Okay. So yeah, we make this assumption. And that really means like you assume it's a normal distribution, or you assume it's like a Laplace distribution, or you assume it's a Bernoulli, which might not be the case all the time. But if you do all this, then you say, okay, like in reality, I really just got a fixed data set. And what am I going to do with that fixed data set? Like, how am I going to use that to get a parameter? because if I can get an estimate of this parameter, I will have an estimate of P of Z, and then I'm good to go. And the idea of maximum likelihood estimation was to say, okay, well, let's maximize this thing called a likelihood function, which really you could think of as just the PDF, the joint PDF of the data. So you want to pick the P that makes the data the most likely. And okay, so here are the steps. You start with this thing called, you want to maximize the likelihood. Then it turns out that, right, like maximizing the likelihood is like a bit of a complicated story. So what you can do is you can write the logarithm of the likelihood, which doesn't change the optimization problem. And then you can change the max to a min just due to convention for optimization purposes. And then because things are IID, you can replace this PDF of the joint data as the product of the PDFs of each individual data point. Okay, so this was like a very important step. This is like what you will almost always do with this maximum likelihood, which is like you start the likelihood, you take the negative log and change to minimization. Then you replace the likelihood with this product term. And the reason this is all very helpful with this product thing is that the log then turns into a sum of logs due to the log properties. And then at this point, you're just left with this function P of Z, like a sum of functions, but like each one of these is based on a parameter W in the way that you made an assumption what this is, right? So you started with, I assume that the underlying PMF or PDF has some, is a function based on some parameter. I don't know what the parameter is, but I know what that function kind of looks like. Like it might be like the normal distributions PDF or the Bernoulli's PDF or PMF. And so then I can just plug in that function here. And that's just based on some parameter. And then all I have is a function based on the parameter. And then I can just minimize that. And it's a sum. So that's pretty easy to minimize a sum. It's just like if you take derivatives, it's going to be the derivative of each term one by one. You don't need any product rule or anything. And yeah, so you're really just left with this optimization problem at the end. The difficulty was breaking up the product into a sum with the log. And the other thing is like making an assumption that this is based on a parameter. But once you do all that, you're kind of good to go. Then you just have an optimization problem. So from there, yeah, you can solve any problem you want. So these are the important steps to remember. And then we did the same thing for our case, which is this conditional PDF, right? We were doing regression. We wanted the conditional PDF of the labels given the features. And so it turns out our setting is very similar to the MLE setting, which is we have this data, it's all IID. It turns out we have, okay, then we would actually get an estimate of the joint, but then it turns out since we assumed that the conditional is the only thing that's based on a parameter, and it's based on this, like, we assume it's a normal distribution, and its mean is this linear function, and we don't know this parameter W star. So our goal is just to find W star. Like, in particular, because we assume this, what that means is that the PDF of the conditional of y given x, like the labels given the features, has this special form. It's a function of some parameter W star. And that's the important thing, is that we have a function, and it's a function of some parameter. And if it's, then we can just optimize over the parameter. And so that's what we did. We just went through the procedure essentially as above here. You do this, and then what you find is that WMLE, so the maximum likelihood estimate of the parameter W star, that's what WMLE is equal to solving this optimization problem, which is essentially what we've been doing before. So this was like the kind of nice observation, was that this is almost exactly L hat of W. It's only different by, so there's the only thing that's different is that here it should be an N over 2. But since this doesn't change the arg min, we didn't include it. Oh. So yeah, this was the beautiful kind of observation, is that under this assumption that the conditional distribution of y given x is a normal distribution with a linear function as the mean, you get back that WMLE is just exactly the same as the optimization problem we've been solving back in ERM with this estimated loss and so on. And so if you then plug that back into the F-Bayes business, so if we plug it back into here, and we plug in our estimate of this, then we get back that f base is approximately equal to this linear function where the parameter is estimated by WMLE. And so we find that our previous linear regression solution, where we just started with an estimate of the expected loss, actually turns out to be the same as this solution. And that, yeah, that's kind of a cool observation. And it also gives some, like, I guess, confidence that we're doing something reasonable, if two approaches kind of give you the same result. Okay, and then we finally finished the last lecture on this map stuff. It's called maximum a posteriori. And this is just another way to estimate the parameter that describes this conditional PDF or PMF. And just like in general in statistics literature, this is just another way to learn, or like to estimate a PMF or a PDF. And that means estimate the parameter that describes it. And the idea here was actually to, okay, so the review was like, in MLE we did this. So in MLE we wanted to find the parameter W that maximizes the likelihood of the data given the parameter. That's what you think about it as. So it's, yeah, the parameter, find the parameter that maximizes the likelihood of the data. But in this maxima posteriori, you should think of, you're trying to find the parameter W that is the most likely, right? So like now it's not the data that's most likely, but it's the parameter that's the most likely given the data. Okay, and like, yeah, this thing can always seem a little bit foreign of like what exactly that kind of means. And the way to think about this was that W map, well, you can decompose it in this way. So like this is what W map is, right? It's exactly this thing. It's the parameter, the map parameter you're going to learn. And then if you apply the definition of conditional PMF or PDF, this is just the definition of it, and then you apply the product rule above, you get something like this. And you notice that the denominator has nothing to do with the parameter, so you can remove it. And you're left with the following optimization problem. And you notice that the first term is just the likelihood, and the second term is this thing that is the PDF or PMF of the parameter. So you get likelihood times prior. So it's almost the same as MLE, except now you're basically scaling everything by some prior knowledge of a parameter W. And here we actually treat the parameter as like a random variable. Okay. And yeah, so this is just another thing. And then once you have this optimization problem, you can just solve it in every way that we've been, just like we were doing before, except now you have to make an extra assumption on what is the PDF or PMF of our parameters, so P of W. And once you do that, you can solve things. And the procedure to do that is you apply the log, which doesn't change the optimization problem, and then you make it a negative and you change it to a minimization. So minimum of negative is the same as maximum of the original. And the reason that's nice is because now the log breaks up this product into a sum of two things. And this first term is exactly the thing that was in maximum likelihood, and the second term is just this new prior that you need to work with. Okay. There's a couple observations. So like, yeah, this is a typical procedure. If you want to solve some map problem on the midterm and stuff, you should know this thing, which is like that. Okay, so I think on the formula sheet, you have the W map equals to this and maybe this or something like that. But like, yeah, these are just some simple steps. And then, yeah, you do the procedure where you take the log and you get to this. And then after that, you just plug in the definition of these things. Like these things are part of the assumption. So in like the midterm, it will be telling you what distributions you assume that these things follow. Like what are the PDFs and PMFs and what do their functions look like? And then your job will be to actually like evaluate things and stuff like this. Yeah. Okay. And then there was some observations, and these are probably useful to know too, which is that you find that when n gets large, then W map is approximately equal to WMLE. Yeah, we saw this in like an example in the previous lecture, which is that like when you get the solution W map, that solution looks exactly like MLE if n goes to infinity. If the prior on the parameters is a constant, then W map also looks like WMLE. And you can easily see that from here, because if this is a constant, it does not affect your optimization problem, and you're just left with the MLE problem you had before. If the variance is large, then it's also approximately the same. And you can also just see it from here, because if the variance is really large, then this term is also approximately just a constant. And so you can just remove it from the minimization. And then finally, if the variance is small, well, then what you will find is that this thing here, okay, well, I guess we really should go back to the example from the previous class, but you'll find is that your prior knowledge dominates everything. Is that like, if your variance is very small, then that kind of means your prior, this guy, you're very, very, very certain that W is of some certain value. So it's, yeah, so your W map then just becomes the expected value of your prior. Okay. And yeah, and then to finish, what happens is that we use this map method to also estimate the conditional PDF of the labels given the features. And that just looked like the MLE setting, which is you had data, feature label pairs, or IID. And you assume that the conditional of the features, or sorry, the labels given the features is normally distributed, with this like mean being this linear function. And that implies that the PDF has this special form based on a parameter. And here's the new thing for map, which is that you assume that the parameters, okay, so these are your weights or your parameters of this linear function here, also have a distribution. Your knowledge, or what you kind of would want your parameters and weights to be. And so here, a standard thing to assume, or like the case we covered, is that if you assume the weights are normally distributed with 0 mean and some variance 1 over lambda. And here the 0 mean you could think of as like your prior knowledge that you think that the predictor should be simple. It should have, the weight should be close to 0, or like exactly 0. And like the lambda here kind of tunes how confident you are in this. So if you really think that the data should be modeled by a very simple predictor, then you would make lambda very, very large, and you'd have very little variance. And then that basically says that like you're very, very confident that WJ has just almost all the weights are 0. But in the other case where you're not very confident, or you think that maybe the output should be very, like a much more complicated function, then you would make lambda quite small. In reality, what you do is you just try all these different lambdas. This is like the hyperparameter sweeping thing. And then you see which one does the best. Okay, so this was like this. You make an assumption on these parameters' weights. And then once you do this, the stuff we saw above, right? You do these steps to solve for W map, and you end up here. And then for this P of W, you just plug in what you assumed for these guys. So these have a PDF, right? It's the normal distributions PDF. You plug that in. And yeah, so we did this in the last class. So W map then became, you just solve this problem, and it became the following, which turns out to be exactly the same up to like this constant term n over 2 scaling. But that doesn't affect the minimization as just the regularized estimated loss, as just minimizing this regularized estimated loss. And so we found that f-base now through the map estimate turns out to just be the linear function where the parameter is W map. And this is exactly what we saw when we added regularization. So you can think of regularization as doing map estimation of this like conditional PDF with some prior on what the weight should be. And this prior is saying that, oh, we for some reason think that the weight should be close to 0, which is really what we did in regularization. We said like the weights should be close to, like if we want something simple, the weights should be close to 0. And the more confident we are, the bigger we would make lambda. Okay, so that ends, okay. And then there was just, oh yeah, the final thing was this lasso regression, which is just if you change your prior to be Laplace instead of normally distributed, you get something that looks like the regularization business we saw, but now with an absolute value instead of a squared here. And this turns out to be called lasso regression. Yeah, and if you to get this, it's really simple. Like it's the same process to calculate this stuff. And maybe you might have to do something. You might have to work out this step on the midterm. But yeah, you should know how the steps works, I guess, is what I'll say. Okay, and now I'll answer our questions in the last few minutes, which is, does the midterm contain only topics you have talked today? I'm not entirely, I can't answer that fully because I haven't finished making the midterm yet, but I will say that like this is definitely the main things. I tried to pick out the things that are the most important. And then, okay, there's a bit of confusion about the prior knowledge is derived from, and the prior knowledge is just like, yeah, it can be from anywhere, which is like, if you, maybe you just visualize the data or someone told you before, or you just like, for some reason, think that things should be simple, so then you pick the lambda to be larger, Or like you can just not think of it as prior knowledge at all and just say like, I don't know what it is, but what I can do is just try a bunch of lambdas, which kind of happens in practice actually. People don't really say like, I have prior knowledge. What they do is they just run their learner with all sorts of different lambda values. So they sweep like over 10 different values, see how it does on the test set, and then just pick that one. So that's like, I mean, that doesn't really mean you had any prior knowledge. That's just like you tried them all and then you picked it. But you can think of it as like the one you pick is, it can be interpreted as like the case where like the prior knowledge was that these things were small. So it's like weighed by this amount. And yeah, and this like, there's this question of like, wait, if the weights are 0, wouldn't you always predict 0? So the answer is yes. So it's just determined by like, you say like, oh, I think the weight should be around 0, so I don't think it should be like biased to be more positive or negative. But this variance tells you like, how close to 0 do you think it should be? So if lambda is really large, then you say it should be really, really close to 0. So they shouldn't be too large. And if lambda is very small, then you say, okay, maybe the weights can be quite large. And that would, yeah, that turns out that what that means is that this linear function, the mean, can be a much more complicated looking function. Okay, and like, yeah, in general, you can make these like polynomial features as well, and then things get more complicated. Okay, I think that's everything I have for the midterm review. Hopefully that helps. As I said, the tutorial today I think should be helpful as well to cover what's actually useful from the coding assignments. And then I will post a couple more exercises in the course notes over the weekend. And then, yeah, feel free to ask anything on Piazza, and have a good reading week. Thank you, everyone.